First, I thank the organizers for giving me this chance to give a talk about my study. And the title is Multisecant lines and regularity. So you can easily expect what is the relation between these two invariants. Okay, so for projective scheme, I skip the definition of regularity, and here I will denote M over X for the maximal degree of minimal generators. So the ideal, so one basic property of regularity is it provides an upper bound of M over X. And also today I consider the integer L over X. It is defined as the length of maximal multisecant line. So here I consider the length of X intersection line, where our line is not contained in X. So by an elementary consequence of Bézo's theorem, M over X is bigger than or equal to this integer. And in some well-known cases, but the regularity can be understood by the existence of some multisecant line. And so today I want to provide such kind of some examples. But I mean, regularity can be realized by multisecant lines. First, I want to remind you of a classical and beautiful result by Eui-Sung, Rajaspelt, and Peskin. Who proved that the regularity of integral curve is bounded by this integer. And if d is bigger than or equal to this number, then the regularity is maximal if and only if there is a multisecant line from which we can realize the low bound of regularity. And as you know, the first theorem for last 30 years, many people tried to extend the theorem to higher dimensional cases. And recently I heard that some people discovered some counterexample about higher dimensional analog of regularity of the first theorem. And today I want to speak about some generalization of second part for even for zero dimensional case and for higher dimensional case. Okay, so first try to generalize the second theorem was by Bertin in the early of 2000. Okay, so from now X is variety and the dimension will be n and codimension C Then Bertin considered the case where the smooth variety attains possibly maximal second line. And she proved that then X is a projection of a variety of minimal degree. So in general, projection of smooth rational domain scrolls. And then for those varieties, what I mean, isomorphic projections of varieties of minimal degree, she proved the regularity bound. Okay. So this is a rare case where all dimensional, for all dimensions, the regularity is explicitly known. So for smooth case, she could classify varieties having some d minus codimension plus 1 second lines, and then I think that classically people believe that L of X for all integral varieties, L of X is bounded by this number, but as I know, this is still unknown. And anyway, she could prove the bound for smooth case. Then she claimed that if X is singular, possibly singular, and L of X is, here she assumed that L of X is bigger than or equal to this number, and then she proved it, and hence L of X is also bounded by this number. In this way, she could prove the expectation for smooth case. And then she claimed that even for singular case, if X satisfies this inequality, then X is a cone over some smooth variety with maximal second lines. And this claim is wrong, and I want to give here an example. This is in some sense a starting point of this study. So let X tilde be the be a rational normal surface scroll, and I want to project down it such that here there are two sections, and I want to project down the first section to a plane curve. So its degree is A, and the second part isomorphically. Then it is embedded in P3, P plus 3-dimensional space, and here, because I produce a plane curve of degree A, L of x should be bigger than or equal to A. It has many A-secant lines. And this number is exactly the degree of x minus codimension of x plus 1. And obviously x is not cone, so we have many examples with extremal secant line, but it is not cone over some smooth classified variety. So in this year, Ajushi Noma proved the following. If x is locally Cohen-Macaulay, then indeed this expected inequality is true. So now the remaining question is to remove this condition about the singularity of x. Just integral projective variety. As I mentioned, recently some people construct counterexample to regularity conjecture, but I don't know if this is also failed to be true by their example or not. But anyway, from this example, my colleagues Brodmann, Peter Schwenzer, and Wansok Lee started to study some varieties with many extremal secant lines. So we consider,
I cannot understand your question. In the theorem of Noma, 2005, x is locally Cohen-Macaulay.
yes.
If x is integral, then it is locally Cohen-Macaulay.
In curve case, it is true, but in general, it is not true. For higher dimensional case, for curve case, it is already known by Eui-Sung, Lazarsfeld, and Peskin's result. So we first want to investigate how many this kind of multisecant line can exist. So I take the close of this set, And then in the second part of Grosjean-Lazarspelt-Peskin theorem, it is shown that if the regularity is maximal, then there exists some multisecant line, and even one can prove that the multisecant line is unique. It has only one multisecant line, except if the curve is a space curve and it is contained in the quadric. Anyway, so it is generally true. The uniqueness is generally true, and by using this uniqueness, existence and uniqueness, one can show that this set has dimension at most 2n minus 2. No, here, sorry, here n is the dimension of x. Sorry. So if x is curve, then this number is 0. So that means the idea is very simple. If you take general hyperplane section of x and consider the same kind of set, then this is in the Grassmannian, this set is just the intersection of the set of multisecant lines and the set of lines on the hyperplane. So very obvious. And then for general H, if you take this intersection, then the dimension decreases by 2 for general H. That's very well known fact. So if you cut X until you get the curve, then you have a chance to use the result by Grosjean-Lazarspelt and Peskin, and so you get this bound. So here the coefficient is 2 because by that kind of intersection the dimension decreases by 2. And the maximal case is from the proof exactly when the general curve section is a curve of maximal regularity in the sense of Grosjean-Lazarspelt and Peskin. So if codimension is bigger than or equal to 3 and the degree is codimension plus 3, then here I get all varieties with a big regularity. Now we can't expect the equality. But anyway, inside this large set, again, depending on the dimension of this set, we have these 10 minus 1 cases. And at least to me, this case is also interesting. What I mean, the dimension is minus 1, that means X has no extremal second line, but the regularity is maximal. And you may construct easily such example by using, again, scroll. Consider this kind of threefold scroll, and let X be divisor. So here D is a given integer, then we take an integral divisor linear in this class. And then you can easily see that this has this kind of maximal regularity, and so one can easily see that this line section is the only possible line with multiple lengths. So if this line is contained in X, then there is no hope that X has a trisecant line. So, and you can easily construct an example where this line is indeed contained in X. So at least to me this example was interesting because we can see why this can be possible for higher dimensional. This line can be contained in X properly if X has a dimension bigger than y equal to 2. And in that case, the maximal regularity can happen without a multisecant line. So after understanding this situation, then we tried to classify all maximal case. What I mean, the sigma of X has a maximal possible value. So if X has sigma of X has this possible the maximal value, then we call X variety of maximal sectional regularity, and you can understand why we call X sectionally maximal regularity, because indeed this general curve section has really maximal regularity. So our main result about this material is to classify all such varieties, and I provide already one example by projection one section of a surface scroll to plane curve. Bilateral projection. So again, by using some known result for curve case, one can, so this is the starting point of the classification. We can show that such an X can be obtained by as a image of projection of variety of minimal degree. And this is also kind of corollary of curve case. And to show this fact, consider the normalization of x and let L be the pullback of this variant line bundle. Then Eui-Sung, Rajaspelt, and Peskin's result says that maximal regularity curve should be smooth rational curve. So its genus is 0. Wow. In the sense of Tarkov-Fujita, the sectional genus of X is 0. Then obviously the sectional genus of this polarized pair is also 0. And here the sectional genus 0 does not imply that it is a minimal degree variety. But if a normal variety has a sectional genus 0, then it is a minimal degree variety. So this can happen only when it is a projection of a variety of minimal degree, or in general projection of a scroll, rational domain scroll.
So no matter the center is inside one or outside?
It's a proper morphism, not inner projection.
So
maybe birational finite morphism. Yeah, out projection. Yes.
But interface is also purely birational. It can be birational if
Yes,
the
yes.
point or linear space meet with X, that it can be birational.
Yeah.
So
But
it can be. Otherwise, you should say birational out.
No. Here I take normalization, so this map should be finite map. Here I start with normalization of X, and then I could show that we could see that this normalization is really is a kind of projection, and then that should be out projection.
In the proposition, you mean it's a morphism?
Yes. Sorry. So linear projection morphism. Okay. Yeah. Sorry, here I need one more definition. I get the all in the ambient space. I get the all multiple second lines, and then take the closure. The first case is where there is some plane, some n-dimensional plane such that its intersection with the x is a hypersurface of degree this number. And then if you take some hyperplane general linear curve section, then this hypersurface provides d minus c plus 1 second line. And this is first case. And there is some exceptional case. An exceptional case, only one exceptional case. The codimension is 3 and x is contained in some special scroll as a divisor. And this is this single example is much easier to understand if you just consider the 5-dimensional, the smooth case. Then and this is a threefold Regularity. So it has a 2-dimensional family of line sections, and if the divisor class is this one, then any line section will give extremal second line to x. So in this case, x has a 2-dimensional family of extremal second lines, and the difference will be as follows. In this case, because the second lines are all contained in some linear space, so if x is a surface, then the two extremal second lines should meet because they are coplanar, and this is an exceptional case. All extremal second lines are disjoint. Anyway, so eventually there are these two cases, and the example what I provided is included in type 1. It's obtained by projecting the scroll.
That fx is not irreducible in general.
So now it is indeed irreducible. Sorry, no. Here this is f of x. So you can. So it is not obvious from the definition, but eventually here f of x is a linear space, and here f of x is this irreducible scroll.
In proposition G not equal to 0, G not equal to
here x is maximal sectional regularity, so its general curve section is of maximal regularity, and then in GLP it is shown that maximal case is exactly rational, smooth rational curve with some extremal second line. Yeah. Sorry. So I only consider surface case, and what one has to do then it is nowadays very popular way to take a linear projection from this line. And here, because of this length, if you project down, then the image is minimal degree. So if
general means if there is only one decimal second line.
no. It's now it's surface case. So I take a general hyperplane section of the surface, and then it has a unique multisecant line.
Yes.
And that in that sense it is general. Yeah. So this is from general hyperplane section of X. Sorry. So we can, if degree is bigger than or equal to 5, then this is a scroll. So here. So it's very strong tool to take a linear projection of such a surface or variety and then get a minimal degree surface. So our X is indeed contained in this fourfold rational normal scroll. And if you read the Eui-Sung-Peskin's paper, then you can see that the curve case, maximal regularity curve is contained in some threefold scroll, such that this part, this line is exactly the multisecant line. And in our case, okay, so this fourfold is anyway cut out by quadrics, and that means now all multisecant lines of X are also contained in this fourfold scroll. So indeed, f of X is also contained here. I just want to provide some starting point of the proof. So after getting this fourfold scroll, we have two cases. The integer b subscript l is 0 or positive, and
L is the choice of L.
indeed it is independent. It is determined by X. But we know from the definition what I mean. Eventually, it is shown that BL depends only on X. It does not vary. And in this case, already this part is a plane, and then one can show that this plane is exactly f of x, and it intersects with x on a plane curve. And in that case, by some complicated small corollaries, small lemmas, one can prove that this should be 1 and C should be 3, and the most crucial fact is that f of x has then dimension 3. And even our x is entirely contained in f of x. And in the proof, anyway, in the proof of case 2, but only one line is not enough to conclude the classification. So we take another line, and then the intersection contains both x and f of x. And in this case, anyway, it is already shown that C is equal to 3. So that means that these are just hyperquadratics. So the intersection is a Cohen-Macaulay scheme of dimension 4. And well, they are essentially defined as a cone or join. So the join of these two lines is contained in this set, this intersection. Okay, so this is a degree 4 scheme, and it contains a linear space. So it is union of linear space and some irreducible set of degree 3. And in that way, we could prove that this is degree 3 irreducible variety. So now there are 3 possibilities, as we know, and then we exclude these 2 cases and we get this fact. So in that kind of many elementary ways, we could find out all varieties of maximal sectional regularity. And okay, so we could finish the classification, and then next question will be, so what is the regularity of the exact regularity of x? And essentially, x is a projection of rational normal scroll, but if there are many singularities, then, as I know, there is no way to determine the regularity yet. So we could determine the regularity only for surface case. Type 1. Type 2 is rather easier. It divides over some scrolls. So we focus on type 1. In this case, this degree cohomology, H1 cohomology, is not 0, and this means this already means that regularity of x is bigger than y equal to minus r plus 3, and it's different from curve case anyway. And the x is linearly normal. And we could show that from the definition, the regularity is bigger than y equal to this number, and we could prove that its regularity is exactly t minus r plus 3. And one can think that this is an obstruction of lower regularity, and so it may be a natural question if x satisfies some fine normality or not. And from the regularity, we don't know if this surface satisfies d minus r plus 1 normality or not. And so we tried to compute many examples by singular, and then we could see that all examples satisfy this normality. So it's a quite different kind of example. I mean, the regularity is defined by the structure sheaf, and the normality is better than what one can expect from the regularity. But this type 1 means x is has a plane curve. Sorry, so here I should also say that this kind of x is obtained by projection variety of minimal degree, such that some device collapse to some hypersurface. I mean, this has many singularities. Its singularity is even not locally coherent. And we have no way to show the same result for higher dimensional case. Our method is available only for surface case. And your main problem is in surface case, x has only finitely many singularities, and for higher dimensional case, the singularity has positive dimension. Anyway, that's our the problem of our method. Well, at the beginning, I mentioned the Eui-Sung large Peskin's result, and then I said that I want to speak about two generalizations. So about this generalization and about finite dimension, finite scheme case. And so let me shortly mention what I could prove. Well, arbitrary finite scheme may not be interesting because if you start with the integral curve, for example, then its general hyperplane section will have very good properties. But anyway, yeah. Length this number. As I know, Eui-Sung classified the borderline case in order to study the regularity bound of threefold, fourfold, or higher dimensional varieties. Anyway, as a byproduct, he could classify the borderline case, and recently we could show that this property holds even for more cases. So if the degree is bigger than or equal to this number, then there should exist some multisecant line from which we can realize the regularity. So this can be generalized to more cases. And in the proof we could guess the borderline case, what kind of configuration should be for the borderline case. So we could construct the following example. Shows that this condition cannot be weakened. So start with two linear spaces, and here take gamma 1 as an intersection of smooth conic and general plane curve of degree s plus 2. So this has length 2 times s plus 4, and here gamma 2 is the coordinates of this space, and then its length is c plus 2s plus 2, and we could prove that the regularity is s plus 3, or we can express it as half of this number. And the defined equations, the maximal degree is s plus 2, and by our construction L, gamma is equal to 2. So you can see that here this number is smaller than this number, and indeed there exists some scheme whose regularity is not obstructed by multisecant lines. And okay, so in curve case, the maximal case was classified by Eui-Sung, and Peskin, and in 2009 Atsushi-Noma also classified the next case. What I mean, if the regularity is next to maximal, then there should exist a multisecant line. And on the other hand, in GLP, the authors conjectured that if the regularity is big enough, then they conjectured that it should be realized by the multisecant line. And what I want to say is here again I consider some surface scroll. And a divisor, t minus c, okay. Then the regularity of C is this number, and this is smaller than this number. And since C is contained in the scroll, L is equal to 2. I mean, if you take some appropriate value of D, then you can see that here this numerical bound is not correct. There are some examples where regularity satisfies this inequality but has no multi-secant line. And as you can see here, the number coincides with this number. So at least to me, for curve case, maybe this kind of phenomenon can occur for more values of regularity, and I think that so at least this number should be replaced to this number, and then and anyway, this kind of study was completed for maximal case and next to maximal case, and I hope that somebody will prove more general result. Okay, thank you.